Okay, so like I said, starting time series analysis focused on decomposition, where we're interested in trying to decompose the signal into various components and then study the behavior of those components. So in this sense, we're going to be considering sets of digitized or maybe just discrete signals that take the form of, we'll have some big matrix X, and it will be equal to a vector of different signals, X1, X2, all the way up to xm. So we will have a finite number of signals in this case, which is then equal to the big matrix where we have x1, which is a function of t1, x2, function of t1, or at t1, then xm at t1, all the way up to t sub big N. So we have x1 and x2 at tn, and then xm evaluated at tn. So in this sense, we are looking at, typically we're going to look at things like displacement signals of vibrating structures. So in that case, we're organizing our signals spatially along the columns and then temporally along the rows. And in each column, X1 might be a sensor in one direction, X2 might be that same sensor, but in a different direction. Or you could organize this so that from X1 up to XQ, let's say, you have all of the sensors in one particular direction, and then Q plus 1 up to 2Q would be in another direction, and so on. You can organize them however you want. I typically like to organize them in like an XYZ format, then repeating for the next sensor, and so on. But the stuff that we study will work either way. Actually, generally the stuff that we do will be independent of how you organize the data. Okay, so big X here is a matrix that contains M samples or M signals that have each been sampled up to a time of Tn, or big N samples with a sampling rate of, do this in red, Fs is equal to 1 over T2 minus T1. Let me rewrite that. And we're going to assume that it's uniformly sampled. So 1 over Tn minus Tn minus 1 is going to be the same as Fs. So we previously focused on just trying to understand what is going on in a signal and what kind of frequency content is contained in that signal. We used a lot of transforms to try and assess and interpret that response. In this chapter, we're going to focus on extracting those components individually and then studying them separately. And in some cases, we will eliminate some of these components and keep only a fraction of them to produce a reduced order model. And so the first technique that we're going to investigate, and we've used filtering before previously, but now we're actually going to explain what it is, and then you're going to apply it in worksheet 6 to actually use it to decompose a signal. So first thing we're talking about is filtering, and here the basic idea is just to remove components that are above or below some cutoff frequency, FC, or inside or outside of a band where you would define two cutoff frequencies that describe the domain of your band. And you can create combinations as well where you might have multiple bands that you want to keep and multiple bands you want to get rid of things. You can do a whole bunch of different things. You can combine all of these different types of filters together. We are just going to look at basic cases here.
When you do the cutoff frequency, is it going to eliminate the below that or above
It depends on the kind of filter you define.
And when we're doing these, with the model, when we pass the cutoff frequency, is it going to remove the frequencies below that or above?
It depends on the function, but for when you're looking at like the Hilbert transform, that's a low-pass filter. Because again, the discrete Hilbert transform introduces high-frequency artifacts that we want to get rid of. And therefore, we just use low-pass filtering to do that. Okay, any other questions? Okay, so if we just consider some generic filter H T, then we can compute the filtered response as, we'll just say y of t is equal to, and in this case, we're thinking in terms of a continuous signal, but this translates over to discrete signals as well. In this case, we'll have an integral from minus infinity to infinity of x of tau times h of t minus tau d tau. So in this case, filtering can be seen as a convolution between your signal x and your filter h. And generally, it's done in the Fourier domain, where we would end up taking the inverse Fourier transform of x hat omega times h hat omega as follows, where the hats here indicate Fourier transforms. So generally, you think of what your filter does in the frequency domain, and you design around the frequency domain, not around the time domain. Okay, we're going to just take a look at what 4 different basic types of filters look like in the frequency domain, and then we will look at some families of filters and have some figures of what they look like at the end, and then we'll do this worksheet 6. All right, so we're going to start with just a basic low-pass filter, which is what I tend to use the most often. And in general, when you have a low-pass filter, what you want to do is you have some cutoff frequency here, f sub c, and basically everything above fc, you want that to have 0 amplitude, and everything before f sub c, you want to have an amplitude of 1, such that you keep everything and don't change its amplitude below f sub c, and get rid of everything above f sub c. And in that case, you are changing its amplitude, setting it to 0. So this is what we would consider to be an ideal filter, and no such filter actually exists. And instead, what we tend to have is some type of roll-off error, where some frequencies just below the cutoff frequency will have a reduced amplitude, and some components just above f sub c will not get eliminated completely. Consider that to be a real filter, what they would tend to look like. And they might have some types of ripples in them. We'll talk about that in a moment. We'll draw it for the high-pass filter, and we'll see it when we look at different families. And so you have to deal with that as well. So depending on the kind of filter, or depending on the application and what you want to get out of it, you're going to choose a different type of filter or a different family of filter. We'll come back to that idea in a moment. So high-pass filter is going to be the opposite of a low-pass filter. It is going to, instead of trying to remove stuff below, or trying to keep stuff up below f sub c, you're now going to want to get rid of that stuff. And then we're going to want to keep everything above f sub c. Again, this is going to be our ideal filter. And then, of course, a real filter is going to have some kind of roll-off like that. And like I said, you can have some kind of rippling effect, which is essentially an oscillation in either the pass or stop band. And again, this here is called a ripple. Okay, next one we'll talk about is the band stop filter. This is a case where you're going to define two cutoff frequencies, which will define a domain or a range that you will want to remove content from. So our ideal filter is going to look something like this. Everywhere outside of that band, we will have an amplitude 1, and inside the band, we will have an amplitude of 0. And of course, the real filter is going to have some type of roll-off. Let me redraw that. So it's never going to exactly be, it's never exactly going to follow this ideal filter. And the bandpass is going to just be the exact opposite of that one, where we're going to want to get rid of everything outside of the band and keep everything inside the band. Okay, let's talk about different types of families of filters. There are many, many different types of filters out there. We're just going to talk about 4, which are kind of the most common ones that are used. The one that I most commonly use is the Butterworth filter, and this is one that has no ripple in the pass band or the stop band. But it does have a slow cutoff. Okay, so looking at just the plot of this Butterworth filter, here's our pass band. As you can see, it's very flat there. Stop band, and stop band extends on beyond this plot. Has no ripples in it, and eventually becomes very flat. However, we can't see that it's flat here, and that's just because it's got this very slow roll-off, meaning the cutoff is slow. The second type is known as the Chebyshev type 1 filter. This is one that will have no ripple in the stop band. And has a moderate cutoff. So you can see in the Chebyshev type 1 filter shown here, we have this rippling in the pass band, but none of the rippling in the stop band. And it has a faster cutoff, meaning that that cutoff decreases at a faster rate than the Butterworth filter. The Chebyshev type 2 filter in this is going to have no ripple in the pass band. And also a moderate cutoff. I'll just scroll down. You can see here that the pass band is now just flat. And the price we paid for that was that the stop band now has ripples in it as well. And then the last type of filter that you'll see is an elliptic filter. This will have ripples in both band, but has a very fast cutoff, which you can see just looking at that bottom right plot. Here we have rippling in both pass bands, but at a very fast cutoff as a result. So I tend to use Butterworth filters because it lacks any kind of rippling, particularly when doing some type of filtering. Well, okay, the kinds of work that we do, we don't want to alter the amplitude of the signal, at least the part that we're trying to keep. And that's usually why we use these Butterworth filters. If you're computing like a frequency response function where you're applying a filter to both the displacement response and a measured force, in that case you can use something like an elliptic filter, and because what happens is you apply the same filter to both the force and the displacement, and then you divide the displacement by the force, you end up canceling out any of these amplitude effects that arise in the rippling. So that's a case where you could use the elliptic filter and not incur consequences from this rippling while still benefiting from this fast cutoff as well. Okay.